Good morning, good afternoon, good evening. My name is John Kingham, and I am the host and presenter for today's webinar. I've been working for Bentley, Nevada for the past 34 years. I started in our Machinery Diagnostic Services Department and traveled the U.S. and the world diagnosing machinery based upon their vibration characteristics. Past decade or so, I've been working as an application and solutions architect. In this role, I help our customers develop condition monitoring and protection solutions for their plants. We are recording today's session, and in order to make these videos worthwhile to you and your colleagues, we ask that you make sure that you are on mute and refrain from broadcasting your video. We're also going to be using the Slido app for questions. As a default, your questions are made anonymously, but if you prefer, you can put your name in. I do always recommend voting for your own question. It gives it extra priority. And as we are recording, we will wait until the end after we stop the recording to pose and answer the questions in the queue. So with that, get rid of that, we will start. So just as a reminder, the Slido app, the address is right here. It will be up in the upper right corner of the slides as well. That's code. So I always like to start off with some visuals as to why we do what we do. We're looking down the barrel of a cylinder, and we ought to be seeing a piston here. And actually, I guess we do see the piston, but it's a bunch.
And I was just calling.
So that was a bad day for somebody. And if we look here, we see the piston rod itself pretty well bent. So my guess is probably had a liquid ingestion event. Tried to compress some liquid, which is very difficult to do. Why do we do condition monitoring? An unplanned first outage can easily cost 10 times more than a planned outage. And that 10 times, as you can see, is a big number, right? So monitoring your compressors allows you to detect trends while they are still small and to take appropriate actions before it is too late. You can address root causes before conditions deteriorate, and you can plan ahead for required repairs. So before we started doing the webinars, I was traveling around the States doing some seminars on introduction of Orbit 60 and so forth. And I'd always ask the customers, are you familiar with the P to F curve? And quite a few weren't, so I do like to go over it just to make sure we're on the same page as to why condition monitoring is important. So the basic idea is you've got your machine running along, doing a great job, right? And then it gets to this point P where an impending failure is introduced. So in this particular P to F curve is for roller element bearings, so maybe it's a pit on one of the balls, right? So the machine is going to continue to operate for some time until it gets to this point here where it has a functional failure, where it stops doing what it is that you want it to do. And there are certain technologies that we use to understand that behavior of the machine. So vibration usually gives us a 1 to 9 month lead time. And I should point out that different failure mechanisms have different P to F intervals. So that little pit on a roller element bearing may take 9 months to manifest itself into a failure. But if you had an oil whip situation, you could destroy a machine in minutes. So different P to F curves for every failure mechanism. Vibration, though, typically going to be the fastest way of finding a problem. Oil analysis, also a good tool, usually gives you 1 to 6 months advance notice. Thermography, 3 to 12 weeks. And then if you're doing a quantitative preventive maintenance task where you're measuring something, that might give you 5 to 8 weeks. Audible noise, 1 to 4 weeks. And I always talk about how, typically Friday, 4:30 in the afternoon is when my customers would call and say, I've had elevated vibration values for a little while now, but my operator hears something different. So it's now time to take a look and see what's happening. So audible noise is an indicator, heat to the touch is an indicator, and then smoke is generally very definitive that you have a problem. The problem with it is it does not give you any time. So we say when we're looking or living down here with audible noise, heat to the touch, smoke, etc., you're living at the bottom of the curve, and you're in reactive mode. So if you're living at the bottom, you're planning on the fly, you're expediting parts, those parts may not be available, your outages are extended, you have a hurry and fix it fast attitude, and you have no time to analyze the failure. So you're bound to repeat that failure again. You have no time to mitigate it. You have a high impact on operations, and there's generally a fair amount of rework. So that's the P to F curve. Now back to recips. Recip compressors routinely experience large cyclic forces. And that's one of the differences between recip compressors and centrifugal compressors. I go back to my times when I first started working. My first job out of college was working on the oil rigs in the Gulf of Mexico. And my roommate, who was a bit of a sassy guy, was told to go up to the drill floor and report back what was happening. We were both brand new at the time. So he goes up and he comes back and he reports, well, it's going round and round and round. And that's what centrifugals do. They just go round and round and round. Whereas recips, you've got the crosshead piece moving and the piston rod moving back and forth. You've got the crankshaft going around. You got a lot of things going on. As these pistons are moving back and forth, that cylinder gas pressure is changing. You're expanding it, you're compressing it, you're expanding, you're compressing, so forth. You've got the inertial force of all this mass moving back and forth. You might have some unbalance on your crank, so you've got a rotating unbalanced force. You certainly have moment forces as it goes around as well, and pressure pulsations when the valves open and close, because they usually don't open and close smoothly. So many different sources for cyclic stress on this machine. So let's look at some of the malfunctions, and the causes are normal component wear, process gas contamination, liquid ingestion. We saw the effects of that in those first couple of pictures. Abnormal component motion, maybe you have excess clearance in your crosshead and it's rocking back and forth. Support system problems. Typically these compressors have been sitting on the pedestal for years and years and years. And oil changes can be messy. The oil seeps into the concrete and degrades it. You might have a support system problem. So what happens? You have valve failures, piston ring failures, rider band wear, pressure packing leaks, and crosshead and pin wear. And this is OEM data that we have. And as I've presented on recips over the last few years, I've asked my customers, are these numbers valid? 50% of your maintenance spend on compressor valves, 20% on piston rod packing, piston rings. I'm going to mute again. 7% on wear bands, 5% on piston rods, something like that. And traditionally, customers have said, yeah, this is pretty good. Last couple of years, I understand the valves have been getting better, and people are not spending quite as much of a percentage on valves, but these are still pretty valid numbers. So here we have our Recip, and we want to, the whole purpose of this webinar is what sensors do we use on one of these. So API has some shutdown parameters it recommends: frame vibration, crosshead acceleration, discharge gas temperatures, and main bearing temperatures. So main bearings in the crankcase. And then we recommend adding cylinder pressure. Cylinder pressure has a lot of benefits, which I'll go into shortly. And along with the cylinder pressure, we like to have a multi-event Keyphaser system. We'll talk about that as well. Along with cylinder pressure, you're going to get rod load and rod load reversal. We believe rod load reversal is a parameter that maybe you don't shut down on, but you certainly alarm on. And as this piston is moving back and forth, it's expanding, it's really compressing gas, and you'll have force working on that piston. We can calculate what the force is at the piston, or we can calculate at the rod here, the pin. And that pin is the weakest part of the system, so that's where we typically want to calculate it. We want to make sure that the stresses are loading and unloading on that pin, because if it's only loaded or if it's only unloaded, it's going to block the hole that feeds it oil. If you don't have oil going to that pin, you'll have metal on metal, and you will have a catastrophic failure shortly. So that's the importance there. Rod position is another parameter we think is important to manage, and it will help you understand the condition of your wear rings. Here are some other parameters that customers ask us for, and we certainly can provide. Cylinder valve temperatures. You'll learn that when you're doing reciprocating compressor diagnostics, a lot of the diagnostics is based on correlation. So our cylinder pressures are going to give us PV curves, which we'll look at and we'll say, it looks like the suction valve on the head end is bad. Well, we look at our cylinder valve temperatures. That is a good correlation to tell us, yes, you're right, and by the way, it's this particular valve. So cylinder valve temperatures are easy to install. They're not that expensive, so something good to add. Packing case temperatures and packing vent line temperatures are also good for correlation, because if you have a valve leak on your crank end, is it a valve leak or is it a packing leak? So if your temperature is increasing on your vent line, that's a pretty good indication that it's packing leak. So you want to make sure that you're addressing the right problem. You wouldn't want to replace all your valves and still have a problem. Some customers ask for cylinder acceleration. We believe that this whole structure is robust enough and rigid enough that you only need the crosshead accel. But if you want to add a cylinder accel, we're okay with that. It is going to get you closer to the valves, closer to the action, but it still transmits very nicely all the way to the crosshead. And then connecting rod bearing temperature, I don't have any slides on that, but essentially you're putting a thermocouple down by the connecting pin, and you have to get that data out, and it's moving back and forth, so you can't have a wire there. So it has to be done wirelessly, some wireless telemetry. It is not an inexpensive solution, but if you've experienced a loss of lubrication and an increase in temperature there, it is well worth putting that measurement on your compressor, because it'll save you a lot of money in the long run. Okay, So I'm going to move on to transducer placement and installation considerations. So here we have a double acting cylinder. We have our process gas is in green. We have our piston here and our piston rod. So we know that this piston is at bottom dead center, and this side is going to be the crank end. This side will be the head end. So the first thing that I want you to notice is that, and this is where our transducer is. So the first thing I want you to notice is that green, there's a path for that gas to always get to that transducer. If the port was right here, a portion of that throw, you wouldn't be getting any pressure information. And you want to get that pressure information to get good graph and good diagnostics. The other thing that I'll have you notice is that we use a double block and bleed valve, and it is made by Keeney Diesel. You can order it from us, or you can order it from Keeney, if you prefer. But it is double block and bleed, a little safer with the two blocks, and then you can bleed the process gas off into a separate container so that you're not exposed to it. So it's a very safe setup. Here is the actual transducer. And I'd like to point a couple things out about it. It was designed and tested to over 2 billion cycles. And that sounds like a lot, and it is a lot. Some transducers that I've worked with, the OEMs say, hey, our pressure transducer has been tested to over 1 million cycles, which sounds impressive until you do the math. I figure a 300 RPM Recip that is working 24 hours in a day is going to go through 432,000 cycles in a day. So that million really becomes less than 2.5 days worth of work for that Recip. So 2 billion is a lot. This fitting is evacuated, so it's under a vacuum. Gives you an absolute pressure reference, so it's not referencing standard atmosphere. The diaphragm is gold-plated for corrosion resistance, and I'll show you a neat slide next. And then the other thing we do is we separate the electronics module from the actual sensor so that we can increase the amount of temperature it can withstand, because the electronics are the fragile part. I also like to point out this O-ring. In this case, we have the black O-ring on, and it's great for everything except for ammonia service. When you order that transducer, you will get a purple O-ring with it as well. And that purple O-ring is to be used when you're using ammonia service. So here are the pictures that I promised you. Here's our transducer after sitting 4 weeks in sulfuric acid. Doesn't look too bad. Here's a competitor's after 4 days in that same acid. Probably not going to get good readings from this one. And I do point out the pressure transducer is covered by our 3-year hardware warranty, just like any other piece of hardware you purchase from us. We have something like 15,000 of these transducers out in the field today, and we're not losing money on warranty claims. It's a very robust and reliable transducer, as you would expect from Bentley Nevada. Couple of points here. I originally made this presentation for our customer care people, and as such, I included part numbers for them so that they could understand, when somebody ordered Recip parts, what they were looking for. So the part numbers are included in this presentation. So the next question that people generally ask is, how do I get a copy of the presentation? And I'm more than happy to provide you with a copy of the presentation. What I ask, though, is that you make that request through your account manager, your Bentley Nevada account manager. If you don't know who they are, please send me a note, give me your company and your location, and I will let you know who your account manager is. So anyway, here's a part number. So if you ordered a 01, you get a 0 to 100 PSI. And then down here I've put a 1X, same but with armor. So if you ordered an 11, you would get that same transducer, but this cable would be armored cable. And you can see there's different pressure ranges. Here's part number for the accessory that mounts the, it's a mounting clamp for the electronics. We also have some Dow 4 electrical insulating compound. And then here's the part number for the double block and bleed Keeney valves. And those Keeney valves are, built specifically for us to mate with this thread design. And the caveat is they're only good up to 4,000 PSI. So don't be ordering a 10,000 PSI transducer and one of these double block and bleed Keeney valves, because that's not a good fit. Okay, so that's my commercial there. Here's a picture of an installation that our projects guys did. Our projects guys are great at building brackets to protect not only the sensors, but also to protect you from getting false readings. So we had a question come up in one of the earlier sessions about the port length. Were there any considerations for the port length? And our projects guys do design the port lengths to make sure that, if it's too long, you'll get recompression of the gas because it never kind of escapes, and it will build up in temperature. So we have to make sure that the temperature never exceeds the temperature capability of the sensor. So that's one of the considerations. The other consideration is that you want to make sure that as the gas passes over the port, it doesn't excite the Helmholtz resonance. The Helmholtz resonance is that resonance when you blow over the top of a Coke bottle and it makes a beautiful noise. It's a beautiful noise when you blow over a Coke bottle, but when you blow over a transducer port, it's going to really fool that sensor. It's not going to understand. So our projects guys make sure that Helmholtz resonance is at least 100 times greater than the running speed of the machine. If they're doing radial bearings, they make sure that the bracket resonance is greater than, 10 times running speed or something like that. So they tend to be pretty beefy brackets. So this bracket has a couple of things that it does. One is it supports that transducer. We don't want that transducer flapping around in the breeze, so to speak. It's also supporting the electronics. And, nobody will admit this, but if you're going to be climbing around on this compressor, there are plenty of people out there that will put their foot on just about anything. And that includes this transducer. So if you build a bracket that is really sturdy, your transducer has a much better chance of surviving somebody stepping on it. So a lot of reasons for having good, solid brackets. Here is an indicator port valve. And I forgot to mention this when I was showing you the cylinder. But, if you don't have ports drilled and tapped in your cylinders, now is not a good time to do that. They should be drilled and tapped by the OEM, because this is a pressure vessel and you don't want to introduce any flaws or areas where it could weaken that cylinder. So if you don't have ports, there are these special valves that are made that allow the gas to come up through the center of the valve and tie into one of these Keeney valves. And that is, it's a standard offering called an indicator port valve, and much less expensive than drilling and tapping anyway. But at any rate, this is a fairly old picture, but again, we made a bracket for the system. So I also talked about when you install cylinder pressure sensors, you should also install a multi-event wheel. And here's a picture of a multi-event wheel that's been installed on the non-drive end of a motor. And it has 12 notches in it, and then a 13th that is, divided in half, so to speak. So when we set it up, we set it so that the keyphaser is looking at that double notch when the first throw is at top dead center. And then we can index all the other cylinders from it. But the reason we do that, and the reason we require a multi-event wheel, is that this is the speed of a crankshaft in one revolution. So, it may register as 298, but at some points it's, as low as 290 and as high as 302. So, as the crank is in different positions, it's doing more or less work on the gas. So it slows down, well, in this case, it speeds up and slows down and speeds up, etc. So, or no, I have that wrong. Slows down. At any rate, it changes speed throughout this path. And if you want to get in and do diagnostics on whether you have a ring leak or not, knowing where the crankshaft is at every moment is imperative. So that is when we would recommend using a multi-event wheel. So you ask, where am I going to mount this multi-event wheel? And I have multi-event band, and I'm going to show you that in a moment. So if you have a flexible coupling, you can't mount this on the motor if you have a flexible coupling, because that flexible coupling is going to take up some of that torsional movement. You can't use an overhung motor either, because the non-drive end of an overhung motor typically has too much runout. Induction motor, just like the flexible coupling, it's going to tend to dampen out that torsional, and non-motor driven designs as well. That's where you're going to need to use a multi-event band on a crankshaft. But if you do have a solid coupling with a two-bearing motor, the standard multi-event wheel will fit on the non-drive end of the motor, just like it was shown in that picture before. If you have a 4, 6, or 8 throw compressor, there's typically sufficient axial space, you need about 4 inches, on the midspan of the crankshaft for a dual track multi-event band. And I should note that the non-drive end of the Recip crankshaft may also be available for a multi-event wheel, but generally it's cluttered with an oil pump, and therefore it may not be suitable. So you have to check and see. This is the multi-event band, and you can see here we've got a double notch here, and we've got a double notch here. So this is a dual track offset, and you need to make sure that you measure your crankshaft or where you're putting this very accurately, because there is a very high or low tolerance for error here. So we need it to be within the thousands. So this band is laser cut out of the sheet steel, and it's bent to the proper circumference, and then is bolted together here to keep it on the shaft. So with this double notch, we would have a probe or with this offset rather, we'd have a probe where one prox probe would be at this location, the other prox probe would be at this location. Here's an example of a band that has been installed on a compressor, and it's not an offset band. We know it's not an offset band because these prox probes are in line with each other. And both of those prox probes will be active. We use standard 8mm prox probes, and we want to see two. One will be the backup, and we'll automatically switch over when they're both connected to the 3500/25 monitor. Okay. I think we had a question the other day as to, why did we need two? And I'll tell you, we do have, I think, a 50-year mean time between failure on the probes. But failures do occur every so often. And if you've got to get inside that recip to put in a new probe, it's just not going to happen until the next outage. So having a second probe, it doesn't add any significant cost, but the value there in case a probe goes bad is immense. So now we'll move on to the crosshead vibration, and we're going to mount our accelerometer right here on the top, and we want it to be in the center of the path of this motion. If we had it like over here, instead, there's going to be times when that crosshead isn't directly underneath it. You get best bang for the buck, no pun intended, with it right over the top of the center. So what crosshead accel do we use? We use a 330425. It has a full scale range of 75 Gs. Other than the full scale range, it's pretty much identical to the 330400. The 330400 has a higher scale factor, but it's only good to 50 Gs. When you're looking for impact events, you want to make sure that, despite the fact that we don't think you're going to exceed 50 Gs, you want to make sure that you have the biggest range there in case you do, and you don't want to saturate the accel. One of the other caveats is, if you're going to use crosshead accels for protection, we recommend putting 2 on per throw and voting them. So these accels have a frequency response of 10 hertz to 15 kilohertz, and if you use a -01, it'll come with a quarter 28 integral stud. If you're international, you probably use an 02, which is a metric 8x1 integral stud. And you always want to have an 05 on the end for multiple approvals, making sure that it is good for hazardous areas, because you're always going to have recips in hazardous areas. I'd also recommend using the 43217 accel housing to protect that probe. Again, you don't want somebody stepping on it. And here's some pictures. Here's an installation. They're obviously using this for protection because they've got 2. So there you have it. And then when you're mounting that accel, it's very important that the surface is prepared properly. So this is for a quarter 28. First, you want to drill a hole 63/100 deep, and then you're going to use a quarter 28 tap, 1/2 inch deep, a 1-inch spot face, 3/1000 deep, and you want to have a surface finish of 32 RMS on that. So that's crosshead accels. Next, we're going to move on to rod drop, and in the past, rod drop measurements were used to extrapolate rider band wear in the vertical direction only. And for rod drop measurement only, a true vertical sensor mounted in the packing case flange along with a phase reference, so a keyphaser, are required. This kind of arrangement is no longer recommended as best practice. That kind of arrangement was developed 20, 25 years ago, before we had the technology that we have today, and it was our best way of monitoring at that time. Our technologies have grown and our knowledge has grown considerably. So, again, if somebody talks about rod drop, we want to move that conversation over to rod position. So, let's talk a little bit about some of the assumptions for rod drop. The distance measurement made at the pressure packing case changes in direct proportion to the change in rider band wear. So here we're making our measurement here, and we're getting this kind of displacement. We're inferring that there is, through similar triangles, that we have this much movement at the piston. But what happens if there's some movement here? Maybe we've got a worn crosshead and it's dropped. So is it piston movement? Is it crosshead movement? We don't know. Okay. Another assumption for rod drop is that gravity is the predominant vertical force acting on the piston and rod assembly. We're going to show you in a few slides that's not always the case. Rod flex is negligible compared to the amount of rider band wear being measured. And that, my next animation is going to show you that that's not the case as well. And it depends on what the diameter of the rod is in ratio to the diameter of the piston and so forth. And then also operating temperature of the piston is relatively constant. We do have a rod drop application note. If you're interested in it, send me a note and I will send it along. So this next slide is an animation of some data that we took several years ago where we heavily instrumented a rod. We put as many prox probes on it as we could, and then we amplified that motion in this animation. But it does go to show that that rod acts like a wet noodle a little bit. So if you're trying to make a measurement at one point in time and trend it, is that rod in compression at all times? Is it in tension at that time? There's a lot of variables, and as a result, it just doesn't work very well. So say no to rod drop and yes to rod position. And here is a rod position system installed. We're going to use 11 millimeter prox probes for this. We use 11 millimeters, we use 11 millimeters, we use 11 millimeters. We don't use 8 millimeters on this. And the probes are true horizontal and true vertical. We don't call these XY, we call them horizontal and vertical for a reason. And we also don't move the orientation away from 0 and 90. It just does not work at 45s. So, again, 11 millimeter prox probes are recommended for all rod diameters. And a lot, if not all, of the rods are coated with tungsten carbide. So we have 12 different proximeter mods for various system lengths. So whether it's a 5 meter or 9 meter system, base materials such as 4140, and then thickness of the tungsten carbide. The most common is going to be 4140 parent material with 10 mil thick tungsten carbide. And yes, we have a mod for that. So another point that you need to know is that if the recips are going to be in ammonia service, again, remember that purple O-ring, you must use ceramic tip probes. Ammonia will attack the plastic that encases the probes, the regular prox probes, and that's not good. And then another thing that people don't always think about is that you have to understand the hazardous area classification inside the distance piece, because that's where the probes are mounted. And oftentimes that area is class 1 div 1. If that's the case, it is going to require this MTL 7796 negative biased barrier. Here's the part number. We recommend that you mount that barrier not at the monitor, but in the local junction box, because then you don't have to run the safety wire as far. Okay? And then the other thing that a lot of people always forget is the low pressure cable seals. You need to get those cables out of the junction, or out of the distance piece, so you'll need those low pressure cable seals. So here is a plot of two throws and rod position. So throw one, there's really no issues, but throw two here, you see that we started off nice, got a compact waveform here, and as time goes by and they run this machine a little longer, that waveform starts to open up. Okay, and I should point out, rod drop is taken at a single crank angle position. So let's just say 283. So every time the crank gets to 283, it takes a DC gap value. For rod position, we are looking at that signal throughout the entire rotation of the crank. So that's what this is. Now don't confuse this with an orbit, because there is no mechanical correlation to the forces that are acting upon it like there is with an orbit. But it is going to give you a waveform. So at any rate, a little bit longer, you see it really opens up and there's a lot of action going on. And it appears to be outside the clearance circle that we would expect. So you probably have some rider band wear going on here that's exceeded its clearances. If I was looking at a rod drop probe, I'd be only looking in this direction. So it would be sitting here, and I'd be fat, dumb, and happy thinking, I still have 10 mils. Well, you don't. Because again, those forces are not always just acting in the vertical direction. Okay? So while we're on the topic of rod position, I need to let you know that you do need to calibrate those transducers. Again, we talked a little bit about the tungsten carbide. That will affect the scale factor. Also, if the rod diameter is less than 6 inches, the scale factor is going to be influenced. So if you have an incorrect scale factor, it's going to give you incorrect measurements. In other words, garbage in, garbage out. So again, I'll note that we have 12 proximeter modifications alone for the 11 millimeter probes. I forget how many mods we have for regular probes, something like 125 different, something like that. But these mods are based on system length, base metal, and the thickness of the tungsten carbide. So you say, John, how do you calibrate a transducer? Well, we have a 3300 XL shaft micrometer kit. It's a strap-on calibrator. Here's the part number. And you strap the micrometer on the rod in the center of its expected axial travel and in line with that vertical probe. You'll adjust the micrometer to the 0 position. You'll put the probe into the micrometer so that the probe face is flush to the rod, so it's touching. And then you'll back the probe out in 10 mil increments. And if you are connected up to the 3500 monitor and you're in configuration, all you have to do is back it out 10 mils, you hit a button, back it out another 10 mils, you hit a button, and the 3500 will automatically record that gap voltage. If you're not, just record the gap voltage on a sheet of paper, and then you'll have to graph it. The 3500 does all those calculations for you automatically, and it tells you where to gap the probe within its linear range, because typically towards the upper end, when you're up at 100 mils of travel, you may be outside of the linear range of that transducer. Okay, so that is rod position. Next, we'll move on to frame vibration. And for frame vibration, we use this 190501 velometer CT. That CT stands for cooling tower. We developed this transducer for, specifically for cooling towers because they have a very low operating speed. So this transducer is good down to 1.5 hertz or 90 CPM. A couple of caveats here. We do want you to mount this in line with these support webs because that's the beefiest part of the frame. If you mount it, say right here directly across from a throw, that's a thin part of the frame, and it could have a resonance that it excites, and then you'll get false information. I was talking with a customer just recently, and he uses 2 velometers on this end and then 2 velometers on this end. So diagonally across from each other, he votes, one of these 2 or one of these 2 for shutdown. But because he's doing this for protection, he has dual probes. Okay? And here's just another picture of essentially the same thing. So we have our transducer here. We do recommend that you have 1 velometer per throw if you're doing this for condition monitoring. If you're doing it for protection, use a 2 probes per throw. And again, here's the part number. I put a -19 here because that -19 option provides a 1/4 inch NPT thread adapter, which makes mounting this very easy. All you have to do is drill the proper hole and thread that in, and you're good to go. You don't have to do the same surface prep that you have to do for the Crosshead Excel. Again, has a 1.5 hertz to 1 kilohertz frequency response, and then there's a recommended cable for it. It comes in standard lengths from 15, 32, 64-foot lengths, and there's plenty more available up to 250 feet. So again, the 190501 velometer CT, accurate down to 90 CPM. And from a condition monitoring / diagnostics viewpoint, we want to see a low frequency of at least half the running speed of the compressor. So if you have that 300 RPM machine, we want to see down to at least 150 RPM per CPM. And the high-pass filter for the velometer should be no higher than half of the running speed of the machines. So for example, if you have a 480 RPM or 6 hertz machine, then the high-pass filter at no less than 3 hertz. So, I'm going to take a little drink of water here. Excuse me. And we'll talk about 3500. So I assume most of you are familiar with 3500 at this point, but it is designed to meet the API 670 standards for machinery protection systems. It does have capability to meet specific safety integrity levels for Recips, specifically SIL 2. All of these monitors are software configurable. They are more than 1 channel per monitor, typically 4. And we have these 3 monitors that are designed specifically for Recips. So we have the 70, which is a 4-channel impulse and velocity monitor. The 72 is a rod position or rod drop monitor. And then the 77 does a cylinder pressure. And those are all 4-channel monitors. In conjunction with these 3, we're also going to use, the standard 25 keyphaser, 2-channel keyphaser monitor, and the /65, which is a 16-channel temperature monitor. So talking about the 70 first, again, specific for reciprocating compressors. And as a result, we want to take synchronous waveforms, 720 samples per revolution of the crankshaft. So every half a degree, we're taking a sample on that synchronous reading. So you get a lot of great detail on what's going on with your accels and your frame velometers. And then we do this filtered synchronous from 3 hertz to 2 kilohertz. And we sometimes call that the knock filter. So you ask, why do we do that? And hopefully I can demonstrate here. But that is an impact. And that's a very low frequency event. But those accels are also picking up all the gas going through the valves. So, which, hopefully the gas is going through the valves, unless they're shut, of course. But when it goes through the valves, it makes a noise. So it's very high frequency. So you don't want to confuse the amplitude of that high frequency noise with that of the impacts. So we filter it for this range, and then you only get the impacts. Okay, and then this is configurable for the frame vibration. We'll do directed 1x, and then crosshead acceleration. We do these band alarms. So you have these 6 configurable band alarms. You've got an overall here, a bias voltage that makes sure that that sensor is okay and working properly. And then band 1 and band 2 are going to be looking for liquid ingestion. So liquid ingestion is going to be either at the top of the stroke, so 0 degrees plus or minus 10 degrees, or it's going to be at the bottom, dead center of the stroke, so 180 degrees plus or minus 10 degrees. So if you have a high band 1 or 2 alarm, you'll know it's liquid ingestion. Bands 3 and 4 are designed to help you detect looseness in your running gear. So your crosshead, or maybe you have a loose nut on your piston, something like that. So they are going to be typically set up for, I believe it's 20 to 55 degrees and 200 to 235 degrees. And then bands 5 and 6 are user configurable, and sometimes we set them up to look for up-running machines that might have some lubrication issues on the pistons. So that's what those are for. And so the key benefits of the 70, again, due to those configurable bands, we can detect liquid ingestion in the cylinder, excess crosshead clearance, loose or cracked nuts, bolts, pistons, and excessive clearance in the crosshead pin bushings. And then from a frame vibration perspective, you're looking for inertial imbalance, looseness in the foundation, and large moments due to excessive rod loops. Again, here are the part numbers. I'm not going to go through those. So that was the 70. Now we're going to talk a little bit about the 72. And the 72 is the rod position monitor. Again, 4 configurable channels. We recommend rod position, but you can do rod drop as well with this. And then if you have a hyper compressor, which doesn't really have a piston, it just has a plunger, you use that for plunger position. And some of the key benefits, of course, the rod position gives you an indication of rider band condition and crosshead looseness. With the hyper, those plungers are typically made out of solid tungsten carbide and they're very brittle. So if they're bending, that is not good because of the brittleness. So you'll understand the bending forces, the packing condition, and of course the crosshead shoe wear. The other thing that we have learned is that when those plungers break, there's usually no indication of that other than it wipes out both of those horizontal and vertical rod position probes. So when those probes go not okay, that is a trigger for a shutdown. Okay. So again, here are the part numbers. And then we need to talk about the 77, which is the pressure cylinder, cylinder pressure monitor. So degrees of rod reversal. We talked a little bit about this earlier. We want to make sure that that crosshead pin is getting proper lubrication. And the only way it gets proper lubrication is if there is rod load reversal. And, you know, the machines are obviously designed to have proper rod load reversal, but if you have a valve failure or possibly an unloader set up incorrectly, you can get into a situation where you don't have good enough unloading. So, and I also like to point out that our calculations are done within this monitor itself. So I've heard of other systems where they feed information from this monitor to a computer system. The computer system figures it out and then sends the data back. Well, you know how reliable computer systems and communications are. Not very. Getting better, thankfully, but still, there is a great opportunity for an error there. We do all those calculations right on board here. So we're also going to calculate peak rod tension and compression, suction and discharge pressures, maximum and minimum pressures, and compression ratios. All of those values can be Modbused out to your DCS if you don't have System 1. If you have System 1, those values and more are going to be trendable. So you'll get crosshead pin load, again, that's rod load, and then suction and discharge valves. If you've got System 1 and you're looking at the PV curves, you're going to have a very easy way of diagnosing whether you have valve leaks. And then piston rings, again, you need that multi-event wheel to give you the added accuracy of the timing, but you'll be able to confidently diagnose piston ring leaks. And here are the part numbers and so forth. And that is the end of my presentation. I want to thank you for participating, and I'm going to go ahead and stop the recording.